Welcome to lecture number 10 for ECE 321 Analog Electronics. In today's lecture, we're going to go through an example of how to design a filter. So, start with the requirements. Requirements are all important. Requirements drive the design. Typical filter requirements look like this. Suppose I want to define a pass band and a reject band. I want the pass band to be between 0 and 100 radians per second, where pass means the gain is at least 0.9 and the gain is no more than 1.2. I've got a reject region over here where the gain has to be less than 200 or less than 0.1 for frequencies above 200. Give me a filter that does that. Any filter that meets those requirements is okay. What this means is that between 100 and 200, I really don't care all that much. As long as the total gain is less than 1.2, I'm fine. So I could have a little bit of resonance in here. Could be Butterworth, could be Chebyshev, your pick. What this one right here says, the gain being less than 1.2, says I could actually have a Chebyshev filter. I could have a slight resonance, or I could have a Butterworth. It's your pick. Another thing is this guy right here, I don't want to bring him in all the way, say, to 101 radians per second. If I did that, I would have like a 90th order filter, and I don't want to build a 90th order filter. So you kind of have to look at what the customer needs, what it is you want to do. The further out I push this line, the easier it is to build the filter. The further it in, the better the filter, but the more poles I need. So how much can I get away with? So let's assume, for whatever reason, 200 and above is good enough for my requirements. 100 and below is good enough for my needs. There's my filter requirement. The first step is to determine how many poles you need in your filter. If I have a single pole, the gain versus frequency drops off as 1 over mega. If I have 3 poles, it drops off as 1 over mega to the n. So what I need is at 100, the gain is at least 0.9. At 200, the gain is at most 0.1. So let's just call this 1, nominally what the gain is. Gain drops off. If I have a single pole, the gain is going to drop off by half. As we go from 100 to 200, 2 poles a half squared, 3 poles a half cubed. The number of poles I need is how many poles do I need so the gain drops off by 90% when I double the frequency. If I solve, I get n is 3.32, meaning I need at least a 4th order filter. From before, it's just as easy to build a 5th order filter as a 4th order filter, so heck, let's make it a 5th order filter. So n equals 5. That's my first step. The second step is pick your favorite filter type. Just remember you got to build it, so pick a filter you can build. For us, with what we know, that would be a Butterworth or a Chebyshev filter. Kind of your pick. I'm going to pick a Butterworth filter because they're easy to design. Chebyshev would probably work a little bit better, but I'm going with a Butterworth. Third, pick the corner frequency. And not knowing really what better to pick, let's make the corner 100 radians per second. So for a Butterworth filter, I'd scatter 5 poles symmetrically with a radius of 100. 180 over 5 is 36 degrees, so each pole is 36 degrees apart. So this would be my filter. That's the nice thing about Butterworth filters. They're pretty easy to design. Now check. Does that meet my requirement? I can do that in MATLAB and kind of show that. In MATLAB, I want to go from, let's say, 0 to 300 radians per second. S is j times omega. My first pole is at 100. Second pole is at 100 at 36 degrees. And a MATLAB exp of j times 36 degrees. MATLAB is in radians, not degrees. So convert that to radians. Third pole is a conjugate of p. Second pole. Fourth pole is at 72 degrees. And the fifth pole is the conjugate of the fourth pole. Oops, I missed. So here's g of s. It's going to be 100 to the 5th power divided by s plus p1 times s plus p2 times s plus p3 times s plus p4 times s plus p5, and check. Does that meet my requirement? And plot the magnitude of GS. Gives you something more meaningful. So that's what my filter looks like. It helps to also plot the requirements. At 100 radians per second and 200, the gain needs to be at least 0.9 and no more than 0.1. And let's put a star right there. So the gain's got to be above this point, below that point, and this filter does not meet my requirement. So what I could do is recalculate the poles, guess again. What's easier is instead of recalculating the poles, let's scale the axis. So let's say, suppose my corner is at 200 radians per second. I would take this curve and push it right to 200, or take the axis and push it left by a factor of 2. Either way works. This is actually easier. If I scale the axis, then the corner is at 200 radians per second, and I meet the first requirement. I don't meet the second one, so that doesn't work. Let's try 150 radians per second. Let's try 110. Let's try 120. Okay, there. That works. If I can't get it to work, I might need to use a higher order filter, or maybe a Chebyshev filter. But this meets my requirement. At 100 radians per second, the gain is bigger than 0.9. At 200 radians per second, the gain is less than 0.9. And this kind of also leads into how you're going to test your filter. When I build it in lab, I'm not going to measure 1,000 frequencies. I really only need to measure 2. I need to go back to the requirements and verify. Do I meet the requirements? Is the gain at least 0.9 at 100 radians per second and less than 0.1 at 200 radians per second? So again, using MATLAB, that was my original filter. After playing with a corner, I made the corner 120 radians per second. That meets the requirement. So that's what the gain should look like if everything goes well. The next step, come up with a circuit to implement that filter. Now I don't know this circuit, but I do know an RC filter, I do know a second order low pass filter, and I know a second RC active low pass filter. So I'm going to build this in 3 stages. So this is what the circuit's going to look like. To find the values, I'll pick one of these guys. I chose 1 microfarad for these, 10 microfarads for this one. Basically, I want the resistance to go up by 10 times as we go from the first stage to the second. For the first stage in black, I want 1 over RC to be 120, C is 10 microfarads, R is 830K, or 830. Second stage, 1 over RC is 120, C is 1 microfarad, solve for R is 8.3K. And notice that R goes up by 10 times as we go from the first stage to the second stage. That prevents loading. To set the angle should be 36 degrees. So 3 minus K is 2 cosine of the angle. Solving for K is 1.38. So 100K, 38K. That sets the angle. So here's the second stage. The third stage. 1 over RC is 120. R is 8.3K. C is 1 microfarad. To set the angle, K is 2.38, making this 100K, 138K. That sets the third stage. And notice this is one of the beauties of Butterworth filters. The poles are all the same amplitude, so I can pick the same RC ratio. Just want to make the first R 10 times smaller to prevent loading. To check the filter, I could throw it in Circuit Lab and find the gain versus frequency. And note, the DC gain isn't 1. The first stage has, or second stage has a gain, the third stage has a gain. So the DC gain is actually 3.28. So let's define this to be 100%. Again, presumably the rest of the circuit is going to add some gain or need some gain. This circuit provides a gain of 3.28 free of charge. So you might as well live with it. To check, I could sweep gain versus frequency to verify and meet the requirements. What I really care about is what's the gain at 100 radians per second, 15.9 hertz. This is 3.08, which is 91%. It needs to be at least 90%. That meets the requirement. At 200 radians per second, which is 31.8, the gain's got to be less than 10%. It's actually 7.8%. That meets the requirements. So from a circuit lab, it looks like this circuit does meet my requirements. If you go into lab and build it, it's kind of harder to sweep gain versus frequency, but what I can do is apply a sine wave in and measure the gain of the filter at that frequency. The 2 points you definitely do need to check are the requirements. At 100 radians per second, I need to make sure the gain is less than 0.9. Again, that's 0.9 of DC. So if this is your input, here's your output. I can calculate the gain. The gain is 2.86. Relative to DC is 87% of my DC gain. If I go to 200 radians per second, here's your input, here's your output. Gain is 0.24, or 7% of my DC gain. That doesn't quite meet my requirements. What I could do is redesign my filter, change the corner to be maybe 110, 115 radians per second, or go to a Chebyshev filter, or make it a 6th order Butterworth filter. What's causing it to slightly differ from what I calculated is this guy right here. There's a little bit of loading first stage to second stage. A third option is I could make this 10 times smaller or this 10 times bigger. That would reduce the loading, get even closer to what I calculated. A couple options you have. A couple things to note. With the requirements, don't go overboard. Again, the requirement that I had is at 100 radians per second, the gain had to be at least 0.9. At 200 radians per second, the gain had to be no more than 0.1. So keep out of this region, keep out of this region, and the overall gain had to be less than 1.2. Keep out of this region. Any filter that does that works. If I take this requirement and push it in, say I want to block frequencies above 110, on paper that looks good, but if you solve for that filter, or make it 120, I'm going to need a 13th order filter. You can build a 13th order filter. It won't be fun, but if that's what you get for the requirements, you might go back to the customer and ask, do you really need to reject frequencies beyond 120 radians per second? Could you live with 200 radians per second? If you could, I don't need a 12th order filter. I can use a 5th order filter. So requirements are all important. If I go overboard on the requirements, that's going to imply a really high order filter. Another note is we used a Butterworth filter. Chebyshev filter would actually work better. It's just a slight perturbation. It's a little bit harder to determine the Chebyshev filter, but if you have a table like yesterday's lecture notes, they're not that bad to come up with. And the implementation isn't any harder than the implementation of a Butterworth filter. And finally, the filter that we designed has a DC gain. I think this had a gain of 3.58. It's supposed to have a gain of 1. I could get rid of this gain, but actually, I might as well live with it. Overall, for example, what we're doing in this course, we're going to take something like your cell phone, have a preamp to get it to a higher level, filter it, drive a push-pull amplifier to drive a speaker. I need a gain for the overall circuit. This part provides a gain of 3.58 free of charge, so you might as well use it. And just compensate by, I don't have to use as big of a preamp to get as large of a signal, the resulting signal to the push-pull amplifier. So again, if you have a gain, DC gain for your filter, it's usually not a problem. So in summary, filter design is fairly straightforward. You need to specify the requirements, and what the requirements typically look like is I have a passband. I specify what frequencies the gain has to be at least something like 0.9 and less than 1.1. I have a reject band. Over this region, the gain's got to be small, and I need to define small. In this case, small is less than 0.1. The number of poles you need is determined by how small is small and how tight this region is. As I pull that left, I need more and more poles. The filter type is kind of your pick. Could be Butterworth, Chebyshev, elliptic. Just make sure that you can actually build it. With what we know, we can build Butterworth and Chebyshev filters. And then you adjust the corner to meet the requirements. With that, you've got filter design. So that's lecture number 10 for ECE 321, Analog Electronics.